Greetings and welcome, internet friends. Mr. Waddy here. We're talking about simplifying radicals today, properties of radicals. You've done some of this before. Sometimes it shows up in geometry classes, dealing with special right triangles, different things like that. But this is going to be the idea. Just like you've simplified fractions, we're going to find a way to write radicals in their simplest form. And so in general, here we go. A radical expression is an expression that contains a radical, right? And so some sort of square root or cubed root or ninth root, something like that, some sort of root. Okay, an expression involving a radical with an index n, and so the index in this case is the 3 or the 9, and this has an invisible index of 2 is what's taking place there. So a square root is the same as kind of the index is 2, second root. And so an expression involving a radical with index n is in simplest form when these three conditions are met. No radicands. Radicands are the inside. Actually, tell you what, let's so the radicand is whatever's on the inside of the radical, have perfect nth powers as factors other than 1. I guess like this is maybe the best way to look at this is down here. So 9 times 5 is the same as 45, and 45 can be broken down into 9 times 5, and 9 is helpful to us because 9 is a perfect square in this case, and this is a square root, so a perfect square is able to be simplified. And so I could break that into square root of 9 times square root of 5. Square root of 9 becomes 3. And the square root of 5 cannot be simplified any further. And so that's one of the possibilities. No radicands contain fractions. We'll talk about today how to deal with that. And no radicals, no square roots or cubed roots appear in the denominator of a fraction. And so we're going to learn how to simplify these today. And the first property we'll have to be able to use is the product property of square roots. And this is similar. It's related to a property we learned a while back. A to the m times a to the n equals a to the m plus n, right? It's kind of related to being able to break apart, properties of exponents, things like that. We also had a to the m times all to the n, equals a to the m times n. And so this is going to behave kind of like that. And the idea is that a square root over a product, I guess it's actually even more so like this property, where if I had ab all to the m, that's the same as a to the m b to the m, where you can kind of distribute this. And so that's kind of what's happening here. The square root is being distributed over all of the factors on the inside. And you can use this forwards or backwards. So you can combine radicals if they have the same index and they're being multiplied into one big radical, or you can take one big radical and break it apart into 2. And so let's take a look at this. Now, I could break this into a whole bunch of different things, right? I could break this into the square root of 2 times the square root of 54, but neither of those help me in simplifying. And so the kinds of numbers that I'm going to want are perfect squares in the case of square roots, perfect cubes in the case of cubed roots. And so what I'm going to be doing is trying to find the largest perfect square that goes into 108. All right, and now it is true that 4 could go into it. It's true that 9, wait, 4, 254. Yeah. 4 would go into it. But we've actually got a better square the best perfect square that could go into this is 36. The largest perfect square that goes into this. And 36 goes into it 3 times. And so it's going to make sense to have a calculator on hand so you can kind of do these breakdowns, and one of the benefits is instead of having a decimal approximation, I'll have an exact representation of this value, but it's in simplest form. Same thing as when we did fractions way back in the day. Simplest fraction form is better than a rounded decimal that represents the same thing. So the square root of 36 is 6. Let's see, I'm not sure what I'm doing with my colors here yet. 6 rad 3. So square root of 3 does not break down any further. Now over here, the square root of 9, the 9's already a perfect square. So that's good. X cubed, I could break into a perfect square. I could break that. The largest perfect square that it could go into is the square root of x squared, and then multiplied by the square root of x, right? Because x squared times x is x cubed. But an x squared I like because it can cancel out with the invisible index of this radical. And so square root of 9 is 3. Square root of x squared at this point we'll call x. We might in a future part of this chapter talk about some different things going on there. And this square root of x can no longer break down. It is in simplest form. And so 3x rad x is what I would end up getting. Also, as far as writing these, this is technically equivalent to the square root of x times 3 times x, but we always write the radical last, because what if this radical bar, this vinculum they call it, I wouldn't want it to imply that it was longer than it was, and so we always write the radical in the last position. Here, let me just take a look at a couple of these. Square root of 24, the largest perfect square that goes into it is 4, and it goes in 6 times. Square root of 4 is 2, so 2 rad 6 is what I would get. Square root of 75, 25 goes into 75, and how many times does it go in? Well, 3. And the square root of n to the 5th, there's actually a couple different ways I could do this. Tell you what, I'm going to write this as n to the 4th times the square root of n. And we'll think about this in a couple different ways. So notice, just agree that, right, n to the 4th times n to the 1st is n to the 5th, right, that I can break that up. And in this case, because this is a square root, I was trying to break the variable into the largest exponent that's divisible by that 2 index. I also, by the way, I could have written it like this: square root of n squared times square root of n squared times square root of n. That's also fine, right? If this whole piece could have been broken down that way. I'll leave it like that for now. Let's see. Square root of 25 is 5, rad 3. Square root of n squared is n, and this one is n. And n times n is n squared. I'm going to write all the simplified parts on the outside first, and then the things that couldn't be simplified, I'm going to write those together under a single square root. And so perhaps you can see, how could I have gotten this to this? Well, the square root of n to the 4th is n squared, because n squared times n squared is n to the 4th. And a square root is asking the question, what multiplied by itself is n to the 4th? And so that's why it becomes n squared. So if you don't want to break it down like this in order to get there, you can just pick the largest even number in this case, because that's going to be divisible by the index. All right, let's keep going. So here's a quotient property. And this is related to our property of exponents, right? If I had a to the b, or a over b all to the m, that was equal to a to the m over b to the m. And radicals and exponents, they're going to have similar properties, and later on in this chapter we'll find out they're incredibly related to one another. And so this is the idea. If I have a large square root over a fraction, I can distribute that square root over the numerator and denominator and then simplify as normal. And so here we go. Square root of 15 up top over the square root of 64. Square root of 15, what's the largest perfect square that goes into it? None. And so square root of 15 is completely simplified. And the square root of 64 is a perfect square, and so I don't have to simplify that any further. Over here, square root of 81 over x squared. So this is the same as, whoa, man, sometimes my tablet does that. It's been weird lately. So break this up. Square root of 81 is 9 over the square root of x squared. At this point, we're calling plain old x. All right, and so you can break these square roots up. You can essentially distribute them over a radical, or over a division, rather. And actually, that's kind of the summary of the first one, too. We can distribute a square root over multiplication or division. Now, this same kind of concept can work when dealing with cubed roots or fourth roots. We're not going to get too fancy. We'll just do cubed roots. But it says you can extend the product and quotient properties of square roots to other radicals. When using these properties of cube roots, the radicands, what's that? The inside may contain negative numbers. So we haven't yet. I think in the next lesson that I've got sequenced, we'll talk about how you can't take the square root of a negative, right? The square root of negative 4 is not 2, because 2 times 2 isn't negative 4, and the square root of negative 4 is not negative 2, so it doesn't work out in that sense either. And so there isn't at least a real number that is the square root of a negative, but cubed roots allow it. Because a cubed root is asking the question, what number multiplied by itself 3 times is this? And I could have a negative times a negative times a negative and have it work out. And so if I'm trying to deal with this, I'm going to pick, similar to when I was simplifying earlier, I picked the largest perfect square to simplify a square root. I'm going to try to find the largest perfect cube that goes into a cubed root. And so I'm going to choose... 1 goes in, but that's not very interesting. 8 technically goes in, but it's not the largest. 64 is going to be the largest perfect cube that goes into this. And I'm going to take that minus sign with it. And how many times does 64 go into 128? Well, that's 2 times. And so I set this up. Now, one of the things to be careful with these indices, the index, all right, is make sure you write it tiny, the size you would as an exponent. I wouldn't want, for instance, the cubed root of 2 is not the same as 3 times the square root of 2. Those are different questions. And so try to get your notation looking good there. So the cubed root of 64 is 8, and the cubed root of negative 64 would be negative 8. Or sorry, 4. I was thinking square roots. You see what I did there? It's all right. Making mistakes. It happens. So negative 4 times negative 4 times negative 4 would give me a negative 64. And you can plug this into a calculator. You just have to kind of hit the second button in order to access an nth root. So I could do 3 second, and then right above the x squared button, you'll see an xth root button as well. So you can play around with that as well. And the cubed root of 2, by the way, does not simplify any further. All right, cubed root. Pardon me, my kids are yelling. Hey, Waddy boys, be quiet, okay? Yeah, it's all right. We're figuring out this remote learning thing. So let's see. Here we go. I've got the cubed root of 125. We'll be able to simplify that. And so x to the 7th. I could break this up into x cubed times x, but I suspect I could just break this up into the largest exponent that's divisible by 3. All right, 6 is divisible by 3. And then left over would be a cubed root of x to the 1st, because x to the 6th times x to the 1st is x to the 7th. All right, so the cubed root of 125, careful, Waddy, here we go, is 5. The cubed root of x to the 6th is x squared. Oh, now I've really got to be careful because I'm going to have an exponent next to an index multiplied by the cubed root of x. I don't want this to somehow look like 23 altogether there. And so that's the simplified version. Okay, let's keep going. So break this up. It breaks up over division as well. Kind of distributes in a sense. Over the cubed root of 216. 216 is the same as 6 times 6 times 6. And so up top, I'll have the cubed root of y over 6. And we're okay with that. We're okay with that. I don't have a fraction left inside of a radical. I don't have a radical on the denominator, which we haven't addressed that yet. It's always conveniently been working out for us so far. Over here, let's break this up. So up top, I'll have the cubed root of 8, which is a perfect cube. I'll have the cubed root of x to the 4th. I'm going to break into x cubed times x, right? 3 was the largest exponent I could get. That's divisible by that index. Over cubed root of 27, that's a perfect cube, times the cubed root of y cubed. And so cubed root of 8 is 2. Cubed root of x cubed is x, times the cubed root of this x does not simplify, over 3y. And so that finished out there for us. Not bad, not bad. Okay, I think I've got, I do have some more I've got to do. Here we go. Let's quickly try to figure these one of these out. Question 10. What's the largest perfect cube that goes into 16? Well, that's 8, and it goes in 2 times. And then the largest perfect cube that goes into x to the 4th is x cubed and times x. And so cubed root of 8 is 2. Cubed root of x cubed is x. I'm simplifying the ones that simplified first, and then I'm going to combine the other parts that can't be further simplified. I might as well put them back in a giant radical altogether. So I'm going to have 2x right there. Just in terms of language, the radicand is the inside, the index is the little outside guy. Cubed root of 54. Ooh, now I'm short on my multiplication table here. I feel like, 27. 27 goes in twice. There we go. This one I could have done 27 times 2, and that would be 3 cubed roots of 2. And it gets a little crazier over here. Yeah, I'll let you guys work on that. Now here's the trickiest skill is how do I get a radical out of a denominator? Because it's not allowed. It's just not allowed. Can't leave no radicals in a denominator. And so this process is called rationalizing the denominator. And the trick is multiply by some version of 1, right? If I take any fraction and multiply by 1, I'm not changing the value. If I take a fraction and multiply by something equivalent to 1, I might change the way it looks, but I'm not changing its value. And so what I'm going to do is multiply by the appropriate form of the square root of 1 that will eliminate the radical in the denominator. And so what would I have to multiply this by to get rid of that square root? Well, watch this. This is actually a nice little trick. If I multiplied the square root of 3n by the square root of 3n, and tell you what, let's explore what happens to that. We'll just deal with the denominator here. There's a few ways I could think about it. That is the same as the square root of 3n all squared, which the square root and the square cancel out. That's one way you could think about it. Another way I could think about it is 3 times 3 is 9, and n times n is n squared. And the square root of 9 is going to be 3, and the square root of n squared is going to be n. And so that's another way I can think about it. And so by choosing something that's going to give me perfect squares to cancel out with the square root, that's good news for me. But I can't just willy-nilly multiply the denominator by this value. I have to multiply the top as well. And so if I multiply the top by the square root of 3n as well, this whole fraction is the same thing as 1, okay? And multiplying by 1, it's not changing its value, it's just changing the way that it looks. And so if I multiply now square root of 3n times the square root of 5, I can just multiply those together as one big radical. So because the indices are the same, I can just combine their insides. So 5 times 3 is 15n. And is there a perfect square that goes into 15? Not that I can think of. And so square root of 15n, like so. Now, it's tempting to be like, oh, I could reduce this. No, super illegal. All right, because one's inside a radical, the other's not. It's tempting to be like, oh, I could cancel out those ends. Nope, super illegal, because one's inside a radical, the other is not. Did we encounter that before anywhere else? No, this would have been the 2/3. Those were both outside of radicals. If they were reducible, you could have done that. Yeah, if 15 and 8 somehow, if this was like 16, well, I don't know, if this was 12 and 8 or something like that, this one's a radical, this one's not. I would not have been allowed to reduce those. So even though I appreciate that you're wanting to simplify things, but it would have been illegal in that case. Before I do part B, I want to take a look at a couple more of these. So what would I have to multiply this by to get rid of the square root in the denominator? Well, square root of 5 times square root of 5 is going to be just dandy, and so I'd multiply by rad 5 over rad 5 because that is the same as 1. Over here, I want to get rid of the radical in the denominator, so I'm going to multiply by rad 3 over rad 3. Okay, over here, want to get rid of this? I'm going to multiply by rad 2x over rad 2x. All right, and tell you what, let's actually simplify one of these. So up top, rad 5 is left over. Rad 5 times rad 5 is just 5. And there's a couple ways that you can think about why that's true. It's because it's the square root of 25, and the square root of 25 is 5. Another way you can think about it is it's the square root of 5 squared, because multiplying something by itself is squaring it, and then the square and the square root cancel each other out. So whichever way you think about it, I'm fine with. And you could arguably even just realize, oh, if I multiply a square root by itself, it's just going to be the radicand. The square root will cancel out. So this one would have been like square root of 30 over square root of 9, which is 3. Right? It's just going to, the radicals cancel out, and it's just going to be the inside. Square root of 30 doesn't have a perfect square that goes into it. This one up top, this one's not in a radical, and this one is, so I can't combine them. So 7 rad 2x over 2x. Now, can the 7 and the 2 simplify? If there was a number in common, I could have, because both of those are not in radicals. Let's see. And this one, tell you what, let's break this up into the square root of 2 times the square root of y squared all over the square root of 3. To get the radical out of the denominator, I'd multiply by rad 3 over rad 3. And so I'll have, let's see, what can simplify up top? Square root of y squared is y. Square root of 2 and square root of 3 I can combine to be a single radical. 2 times 3 is 6. And rad 3 times rad 3 is 3. Can I simplify this? No, because the 6 is in a radical and the other is not. All right, so with square roots, that's the general trick. It's a little bit trickier. What about a cubed root? What about a cubed root? Because whatever I multiply this by, it's going to be a little bit inconvenient for us. Let's consider. Maybe you're coming up with a thought, well, why can't I just do this? Well, what's that going to do? That's going to give me, in the denominator, the cubed root of 81. But the problem is, what's wrong with 81? 81 is not a perfect cube. 81 is a perfect square, and so 81 cannot cancel out with a cubed root. Now, I could have broken it up into this, and this could have reduced, and I'd get 3 cubed roots of 3 in that denominator eventually. But the problem is, I still have a radical in the denominator. I can't leave that there. And so I'm going to need to be much more intentional about what I do. So whatever I do, I'm going to multiply it by a perfect, or a cubed root. But I want to multiply it by something that will give me... Actually, let's write this down. Let's write this down. This is worth doing. Oh, that's like a off-white there. Mult by something that will give you a perfect cube. And so 9 times what would give me a perfect cube? Well, actually, one clever way you could kind of think about this is 9 to the first. If I multiply it by a 9 squared, that would give me a perfect cube. Another way I could think about it is 9 is the same as 3 squared. And so if I multiply it by the cubed root of 3 to the first, a 3 squared and a 3 to the first will give me a 3 cubed, which is a perfect cube. Let's actually, I kind of like that one. The other way you could think about it is just look at your list of perfect cubes, and I realize 9 can go into 27, and so what do I have to multiply it by to get 27? 3. And whatever I multiply on the bottom, also have to multiply on the top, and so I'd have 2 cubed roots of 3 over the cubed root of 27. There it is. Which is the same as 2 cubed roots of 3 over 3. Can this 3 cancel out with a 2? It could have if there was something in common. Can this 3 cancel out with that 3? No, because this is in a radical and the other is not. All right. Well, I think that'll do. So thanks for watching, internet friends. Have a great day.